All right, everybody, I am going to go ahead and make our video for the third day of review, which is our final day of review for the final exam. And this will be your video for that Friday of review week. And I am just kind of taking a shot in the dark at where we will be. I'm hoping that we have covered exam 1 material on the Monday and exam 2 material on the Tuesday, and that, or on the Wednesday, and that today is the Friday day and we are in exam 3 material. So I am looking at this white review that I handed out to you. At the top, it says by Adam Bowden. That's one of our faculty members. He's the one that put this together for us. And as I look at it, I see that on page 3, so that's where I am. You can see we've done rational functions and polynomial functions and stuff like that. When I get down here to the bottom where it says section 4.4, I feel like this is going to be our chapter or our test 3 material. So this is going to be exponential functions and log functions. And then up here, I see some word problems with exponentials and logs. And then down here, we start into our elimination and stuff like that. So I'm just going to pick and choose some because clearly I don't have enough time to do all of that. Plus there's another page, right? There's a stuff on page 4. So that's about exponential growth and stuff like that. So I'm just going to pick and choose a few because clearly we don't have tons and tons of time. And then hopefully this is about a 30 to 40 minute video. And then whatever I don't cover, you can study on your own. There is an answer key to this particular handout. It's the page 5 and page 6, the answer key part. So if I don't get there, work the rest of the problems on your own and then check your answers with the answer key, and that will be great. All right, so just to kind of get us warmed up a little bit, I am going to do number 37. Because as I was grading your test 3, I saw that some of you actually struggled a little bit with this one. We didn't do one quite as elaborate as this problem, but 64 to the x minus 2 is equal to 32 to the 3x, okay? So as I look at that one, I'm like, oh my gosh, that's definitely an exponential equation because the variable is up here, right, in the exponent part. But it's kind of a lot of stuff going on there. And the very first method we learned to figure out with this is maybe, just maybe, those two bases have something in common. So if I can strip those back a little bit and talk about what they are a power of, then maybe I can write these two bases in the same terms. So I know that 64 is 2 times 2 times 2 times 2 times 2 times 2. Okay, there's 6 of them. It's 2 to the 6th. Okay, and if you're not sure, then take your calculator and do 2 times 2 times 2 times 2 times 2 times 2. Okay, so that's 64. And on the other side, I've got 32. Well, 32 is half of 64, right? So just to make that clear, it's 2 times 2 times 2 times 2 times 2. Okay, so if I see these two bases down here and they look like they're both even, or they might be both powers of 3 or something like that, then I'm going to rewrite them. This case, it's power of 2. So the 64 is 2 to the 6th. And that's raised to x minus 2, right? And that's equal to, and we just said 32 was 2 to the 5th. And that's being raised to the 3x, okay? So first step is rewrite this as they're both having the same base. That's almost guaranteed that you'll have one that's kind of like that, where you have a similar base and you just, okay, here we go, no problem. So now I look and I say, well, this is 2 to the 6th to the x minus 2. And remember that we have 3 exponent rules, and one is whenever you have an exponent raised to an exponent, you multiply your exponents. Okay, So that is one of my exponent rules. An exponent raised to an exponent, we multiply the exponents. So I've got to keep the base the same. This 2 is not going anywhere. He's coming down. Okay, 2 to the, but this turns into 6 times x minus 2. And this is 2 to the, and this turns into 5 times 3x. Okay. And so I'm still got the same base. That's the whole premise here is if I've got the same base, then I know these bases are equal to each other, which means I can just look at the exponents, because if the bases are equal to each other, in order for this to be a true statement, the exponents have to also be equal to each other, right? So I can pull those out by themselves and I can say 6 times x minus 2 is equal to 5 times 3 to the 3x. Okay. And now this just becomes solving an equation, which we've done lots of times this semester, right? 6 times x is 6x. 6 times negative 2 is negative 12. 5 times 3x is 15x. So 6x minus 12 equals 15x. And then it becomes a matter of combine your like terms. The bigger x is on the right-hand side. So I'm going to subtract off the 6x and move him to the right-hand side. That'll be negative 12 is equal to 15x minus 6x is 9x. And then we're almost done. Now that I've got this x guy over here by himself, I can say, oh, we're multiplying by 9, so we're going to divide by 9. To get rid of that. Get rid of multiplication by dividing. X equals negative 12 over 9. Or I know that both of these are divisible by 3, so negative 4 over 3. X equals negative 4 over 3. All right. So that is my answer for number 37. I'm just kind of checking along since I have the answers. Yes. He says it's the set negative 4/3. Okay, there we go. Very nice. All right. So that's one where I can just manipulate the bases and I don't have to worry about logarithms for that one. So I'd like to do some stuff where we have logarithms and maybe we need to change between logarithms and exponentials and stuff like that. Looking at 38, by the way, it is another one that I can just manipulate the base. 9 is a power of 3, 27 is a power of 3. So I'm going to skip that one because it's much like the one we just did, and I'm going to go to 39. 39 says log base 3 of x plus 1 is equal to 2. Now on your test, I saw a couple of you try to separate these things out, okay? So that rule, we have a rule that says if I'm if I'm multiplying like bases, then I can add the exponents, right? And some of you on test 3 saw this and said, oh, look, I'm adding. So I'm going to separate this into 2 logarithms or something like that, or I'm going to crunch it together and multiply them out. That rule right there only works when I'm multiplying like bases. So I would have to have a log base something plus a log base something, and that way I have the same 2 bases, right? Then I could multiply these together, but I can't do anything with that. That x plus 1, it's just joined together. It's an x plus 1. It's like one equation or polynomial. You got to leave those together. So don't try to mess with those. That's all together. So if I look at this and I use my little saying that I use, log base answer equals exponent. All this stuff in the parentheses, log base answer, this is my answer. It's all together. So I can't separate that out. So log base answer equals exponent. Okay, so I'm going to rearrange that so that it looks like an exponential. Base to the exponent equals the answer. All right. So somebody said, how do I know when to do that? How do I know I need to rearrange it to make it back into an exponential? Whenever the variable is inside of the logarithm, okay? When the variable is inside of the logarithm, that's when I know, hey, I got to get that guy out. And to do it, I got to make this into an exponential. Okay, so this is the log form. And this is the exponent form, exponential form. That's the difference, okay? Just like whenever I have something and it's like 5, like up here, okay, 2 to the 6 times x minus 2. If I wasn't able to manipulate this so that it had a same base, and that x is up there in the exponent, I know the only other tool I have would be to take the log of both sides of this equation. Okay, so you can take the log of both sides and then you can pull these out. So that is a viable method here. And the reason I know to do that is because the x is in the variable. Well, here I know I need to change this into an exponential because the x is inside the answer and I need to pull that out. It's inside the logarithm here, right? I need it out of there. So rearranging this, the base is the 3. Log base, this is my answer, equals exponent. The exponent is a 2, so 3 to the 2nd equals my answer. So all of this x plus 1 stuff goes on the other side of the equal sign. Okay, and again, just keep that together. It's one big joined guy. You can't separate the x plus the 1 until I get to the point of actually solving it. Okay, once it's by itself now I've got 9 equals x plus 1. Now it's by itself. I can totally get rid of that 1 now, right? Because I'm just going to subtract 1 from both sides. But that's because it's not inside of stuff now, right? It's just x plus 1 sitting out there by itself. So to get rid of the 1, I'm going to subtract a 1. 9 minus 1 gives me 8. 8 equals x, and indeed that is the answer on the solution key. I'm just kind of checking myself as I go. So there we go. All right. So that's how I swap in and out from logs to exponents, right? I don't see one on here where I have to go from exponents to log, but I can use that exact same formula in reverse, and that would work for me. Okay. So what I hear is, well, help me with one of those where I can add or subtract or whatever, because that seems to be where we got stuck. Like the most points on test 3 that were lost were in this section right here. So I'm going to do both of these. I'm going to do number, I'm not going to do 40 because I'll show you 40, but I'm not going to work it. It's log base 5 of 3x equals 1. And I'm hoping that you see very quickly that you can rearrange this. The 5 is your base. The 1 is my exponent equals 3x. And then, well, I guess I am working it because there we go. X equals 5 divided by 3. It wasn't too bad, right? So it was like, oh, I'm almost there. I might as well finish it. So, but that one, I feel like you guys can see that pretty quickly and work it out and be okay. The ones that I'm worried about that we struggled with on the test are 41 and 42. So I'm going to look at 41 here. All right. 41 says log of 3x is equal to the log of 5 plus the log of x minus 4. Okay. Again, treat that x minus 4 as one together thing. We're not going to separate him. He's not part of the adding and subtracting that we're going to deal with, right? The adding and the subtracting happens between logarithms. Okay. And when I look at these, I say, what base is this? This is log base. Technically, it's a 10 sitting down there, right? If we don't write anything, it's the common log. Log base 10 of 5 and log base 10, of this x minus 4 guy. Okay. So because these are, both logarithms with the same base on them, that's what I just verified. They all have a 10 down there. Now I see right here, I've got this addition going on between logs. Remember that a logarithm is equivalent to an exponent, right? So what this is like I'm adding exponents, okay? Well, where did that come from? Well, whenever I did it, I must have been multiplying, okay? So this turns into log base 10 of these two things that were separated by 2 logs. I'm going to cram them into 1 log, and I'm going to turn them into multiplication. So the first thing that's being multiplied is this 5. And the second thing that's being multiplied is this big x minus 4. It's all one piece. Okay. And now I look at that and I go, okay, I've got a logarithm on the left-hand side. I've got a logarithm on the right-hand side. This is a property I feel like a couple of you forgot we have there, okay? Once I've got the right-hand side all crammed into a single logarithm, it's all together now. Now I can look and say, oh, there's that rule. If I have a log on both sides, I can basically drop the logarithms, right? Technically, what I'm doing is I'm doing 10 raised to this guy and 10 raised to that guy because it's a log base 10. So I'm doing that. And the 10 and the log base 10 are opposite operations. So boom, those are going to drop out. So 3x equals 5 times x minus 4. Okay. This is what we're hoping to get things to, something that is a nice, pretty equation that I've been working all semester and I can play with it, right? So we're going to distribute that 5 through. So hopefully this looks like stuff we're used to. Okay, 3x equals 5x minus 20. That's a nice, pretty equation. We can get that guy. I've got 5x over there with the 20. I'm going to subtract him. I know that's going to make my x's be negative, but I'll deal with it, okay? So 3x minus 5x is negative 2x is equal to, left over here is a negative 20, okay? And now I look and I say, okay, I almost got that x completely by himself. That's what I want to do. So what's happening to the x? He's being multiplied by negative 2. So to get rid of that multiplication, opposite operation, I'm going to divide by negative 2. And of course, whatever I do to the left-hand side, I have to do to the right-hand side. So I divide the negative 20 by negative 2. And over here on the left, I just get an x. And over here on the right, negative 20 divided by negative 2 is a positive 10. X equals 10. All right. So there we have it. And the only thing I need to do whenever we're dealing with these logarithm type things is I need to check when I stick this 10 in, log of 3x, well, that's a positive. 3 times 10 is 30. That's okay. Log of 5, that's okay. Log of x minus 4, 10 minus 4 is 6. Log of 6, that's okay. Remember that I cannot take the log of a negative number. Cannot do that. That is bad. It's not in my domain anywhere, right? So don't do that. Okay, now on the test, there was one that was just a little bit tricky, and this is the way it worked. Say it was, and I don't remember exactly what it looked like, but it was something like log of, let's say, x plus 5. And you got like a negative 3. And some of you just said, oh, I can't have a negative 3 and just dropped your value. Actually, that's not true. Be careful because a negative 3 in here, if I put a negative 3 there, negative 3 plus 5 would be 2. Positive 2, I can take log of positive 2, right? So we have to be a little bit careful because what's happened is this particular guy has shifted around. And so his isotope shifted with him. And so all of a sudden, negative 3 would be an okay value, right? Negative 1 is an okay value. Negative 2 is okay. I don't get my isotope until I get over to, oh, excuse me, negative 5. Negative 5 plus 5 is 0, and I cannot take the log of 0, right? If I punch that on my calculator. The log of 0, that should be a vertical isotope in there, right? And it says, oh, you've got an error in your domain. And if you hit go to, it takes me right back there and says you can't put a 0 in the log. Okay, so don't do that. All right, so be careful. It's not that you can't have a negative answer, it's you can't take the log of a negative number. So watch out for that. I did see a couple of you who got stuck on that. On test 3. Okay, and then number 4, I'm going to do this one also because it's right there. Might as well knock it out. It's the log of x plus the log of x plus 1 is equal to the log of 2. Okay, so again, using similar properties, let's see what we can do here. Log of x plus log of x plus 1. these guys are two separate logs that are being added. That means they're exponents that are being added. They must have come from, if I wanted to work in reverse, multiplication. So log of, I'm going to multiply the things that are inside. So x is one of those things, and this x plus 1 is the other of those things, right? And that all sticks together, log 2. All right. And again, I'm looking here and I say I've got a logarithm equals a logarithm, but they're the same base. They're both base 10. They don't say it, but I know they are. So I'm just double checking. Okay, I'm legal. No worries. So now that I have a log equals a log, I can drop the logs, right? And what I've got here is x times x plus 1 is equal to 2. And then again, I can just multiply this out like normal. This is going to be x times x is x squared. X times 1 is a plus x equals 2. Let me move that over. X squared plus x minus 2 equals 0. I moved that over because I see, hey, maybe this guy will factor, and I'm hoping that he does. And so whenever I move him over, hopefully he makes me a nice, pretty number. And sure enough, I should, let me scoot here, should be able to factor this guy equals 0. X and x for the x squared. Two things that multiply together to give me a -2, but add up to give me a +1. So that means it's a +2 and a -1. And hopefully you've gotten really fast at your factoring by now. X squared minus 1 plus 2, that gives me the positive 1x in the middle, -2. Sure enough, I'm good. Okay. So now, again, back to week 1, right? Either x plus 2 equals 0 or x minus 1 equals 0. X equals -2 or x equals +1. Those are my two answers. Okay. But now I go back and I say, hang on a minute, these are logarithms. We have to check our answers, right? And I look here and I say, oop, I'm taking log of -2. Can I do that? No, that guy's got to go, right? I can take log of 1. That's okay. And I can take log of 1 plus 1, that's 2, that's okay. And I can take log of 2. So x equals 1, that's an okay answer, okay? But the x equals -2, that one's not going to work for us, so we have to drop it, okay? So we do on these logarithms always need to check our answers and make sure we're not doing something that's illegal, an illegal function with our stuff, right? Okay. So I think that's a pretty good review for the logarithm stuff. We're going to move on because I'm already like 20 minutes into this video and I need to scoot. So let us look. There are here the word problems. I'm just going to throw some stuff at you. This first one, number 43, is compounded quarterly. And I look at that one and I say that's got to be the compound interest formula. So remember, there are two different formulas. A equals P times 1 plus R over N to the NT. That guy is the compound interest formula. And inside of this, remember, A is my amount in the account at the end. P is my principal. That's the initial amount of money I put in. R is your interest rate. And that's as a decimal. 0.05, for instance, would be 5%. So you have to change them around. T equals time in years. This interest rate is an annual, yearly interest rate as well. Everything needs to line up there. Like if they said 6 months or something, it would be a half of a year, right? And N is the number of compounds. Okay, so that is the background on the compound interest formula. Remember, if it says quarterly, how many quarters are there in a year, or how many quarters in a dollar? 4. Okay, if it says monthly, how many months in a year? We're going to put in a 12 for N. So these are my N values, right? If it said daily, we're going to assume that there are 365 days in a year, okay? So that's if I have an N. That is different from compounding continuously. Okay, compounding continuously, that's a different formula. So this one right here, 43, I would use that compound interest formula because he says compounded quarterly. I would use N equals 4, right? But this one, 44, that one says compounded continuously, right? And that one is the A equals PE to the RT, where the same stuff is going on here. I've got the same A, the same P, the same R, the same T, but that E, remember, he's our new friend. E is approximately 2.72. And you have a button in your calculator that uses that E. He's normally, if you look here on the left-hand side, you've got your log button. Underneath that is your LN button for natural log. And right up there in blue is E to the X, right? So if I use it, I have to hit the second button and then the LN button. And I'm just going to do E to the first power. So we see the value for it is E to the first power is 2.718. And we usually say 2.72. All right, so that is the formula you will use for number 44. So just be aware of that. Okay. And then I'm looking, solve the problem by using systems of equations. I'm going to say that you can set those up on your own. Let me do one of them and then you can do the other. So I'm not going to solve this one, but I'm going to set up the system of equations. 45 says, okay, a bank teller has 51 $5 bills and $20 bills in her drawer, okay, cash drawer. The value of the bills is $780. How many $5 bills are there? So there should be two different equations, okay? And the way we're going to set it up is let X equal the number of $5 bills. And let Y equals the number of $20 bills. Okay, so we have to define our variables and say, hey, which one's which? So what we've got going on here is X, the total number of $5 bills, plus Y, the total number of $20 bills, tells me the total number of bills she has in her drawer. Well, they said that the teller has 51 of them. Okay, so there are 51 bills in her drawer. So $5 and $20. That's an equation. X plus Y equals 51. Okay, I'm done with that. So the way I look at it whenever I do these is not normally I have one equation that talks about the number of the bills, and I have another equation that talks about the value of the bills. Okay, because the next thing that they gave me was the value in her drawer. So let's look. It says the value of the bills is $780. Okay, so I have to do something with these for the value of them. Okay, so if there were 10 $5 bills, then I would say, well, that's $5 times 10 $5 bills. That would be 5 times 10 is $50, right? But the number of bills we don't know. So I'm writing that as 5 times X. You tell me there's one $5 bill in there, then I'll say 5 times 1. You tell me there's 5 $5 bills in there, I'll say 5 times 5. So 5 times however many bills, that will give me the value for the $5 bills. Okay. Plus, how am I going to do that for the Y? Well, you tell me there's one $20 bill in there, and I'll say 20 times 1, right? Okay, if you tell me there's 2, then I'll say 20 times 2. That'll give me 40. If you tell me there's 10, then I'll say 20 times 10. That gives me 200. So I'm multiplying by the number of $20 bills in the drawer, right? So 20 times Y. So these end up looking like the value of the bill times however many bills there are. And when I add those together, I'll get the total value in the drawer, which they said was $780. Okay, so now I guess I will solve this one. Let's go ahead and do it. This will give me a good we'll do this as our system of equations as well. I've got a system of equations. This is how I wrote my equation, but I want to solve them. So it looks like x plus y equals 51 and 5x plus 20y equals 780. There's my system. Remember that you have two different basic methods for solving these. One is substitution and one is elimination, okay? So if I wanted to do substitution, then remember that I would take one of these equations, solve for one of my variables, and then substitute it into the other one, okay? I don't really love substitution, but some people really like it. So you could solve for either x or y, plug it in. Just make sure when you get a number for whichever variable you have there that you back substitute and get a number for the other one as well, right? Okay, so I'm going to do this with elimination, okay? So I see this guy right here is a 5x and I have a 1x here. So I am going to multiply this first equation by a -5, okay? My goal here, if you'll remember, and I'm multiplying the entire equation by that. My goal is to get it so that I can eliminate one of my variables. So when I distribute this through, -5x minus 5y equals, and I don't know what 51 times 5 is. Is that 255? Okay, and it's negative because this guy was negative times a positive, -255. Okay. And then the other equation, I didn't do anything to him, so he just stays the same. Carry him along. 5x plus 20y equals 780. And did you see I just made a copy error? I caught it, but I made the error to begin with. You have to catch yourself. I saw on the test a lot of people who made copy errors and didn't catch their own thing. So your mistake wasn't necessarily in your math. Your mistake was in copying. So double check yourself, look back, make sure it looks exactly like it looked before. Okay. The idea here is I've got a -5x and a positive 5x. If I add these two equations together, those will go away, right? They cancel or reduce or however you want to think about it. So add the equations, these go away. That's called elimination. I eliminated them, right? Now I've got -5y plus 20y, that's going to be 15y, it's a positive, is equal to, and then I've got a 780 and a -255, so 780 plus a -255. When I add that together, I get positive 525, okay? Not quite finished yet, I need that y completely by himself. I see he's multiplying by 15, so I'm going to divide by 15 on both of those. Y equals, divide by 15 gives me a 35. Okay, y equals 35. Not done yet, that's one of them. Y was the number of $20 bills in there, right? Remember that? Okay, so I've got the number of y, but I need to solve for both, so I got to go back, and you can use either one of these original equations you had. I'm going to use the first one because he looks easier to work with. So I'm going to pull this guy down. X plus y equals 51. And I'm going to use the fact that I now know that my y has a value of 35. X plus 35 equals 51, right? And then I should be able to solve for the x by subtract 35 on both sides. 51 minus 35 is 16. Okay, so I've got a value for each of those. If I'm going to put these into an ordered pair, it would be 16, 35. That would be my ordered pair. And whenever I look at the question, remember to make sure you answered their question. It says, how many $5 bills are there? And this was number 45. And we got 16, and sure enough, we are correct. Yay. 16 $5 bills. Okay. So consider that a word problem solved at the same time as we did a system of equations by elimination, right? So if they say use substitution or elimination on the final exam, then you can use either one, whichever one you're used to. but make sure that you can work through the steps, right? So I see that here. I'm looking 47 and 48 on your thing. So 46 is another word problem. Set up the system and then solve. 47, 48 say use addition or substitution. So I'm going to let you work those. We just did one. Okay. 49 says use Kramer's rule or a matrix to solve. Okay. And then 51 and 52 say solve the system by using any algebraic method. So that's any of the stuff that we've done. So I'm going to do one of these, either 49 or 50, and then I'll let you guys do the rest of them because I am running way out of time. Of course, that's the way it works. So, and it says Kramer's rule or a matrix. I'm going to use a matrix just because I want us to get, some work with that. I feel like we kind of got stuck on that one maybe a little bit. The matrix problem on test 3. So I'm going to make sure we can do that. Number 50 is the one I'm going to do with it. And then you can work on 48, 49, 51, 52, and make sure those all look good. All right, so here we go. 4x plus 4y equals -4. That's my first equation. 5x plus a y equals -17. That's my second equation. Okay, so I'm going to solve it using a matrix. Okay. And if you want to look at Kramer's rule, that was in chapter 6, I believe. Well, both of these were in chapter 6, right? There's 6.1, 6.5, 6.5, I believe. 6.1 and 6.5, maybe. Anyway, go and work on those and check them out and see what you can do. All right, so here we go. My matrix looks like 4, 4, and -4 on the top row, and 5, 1, and -17 on the bottom row. All right. And I have a sneaky suspicion after grading you all's exams and seeing that some of you are coming up with the correct solution, but not showing me any work or very minimal work. My suspicion is that you guys were using your calculators and not doing the math yourself. That's kind of what I'm guessing at. So maybe you figured out how to do something on the calculator and then you're like playing with it and then making it kind of look like you did some of the work. So I may be a little bit meaner on the final exam whenever I look at that kind of stuff, because all of these problems have very clear work or very clear directions that say show work. Okay, so make sure you're doing that. All right, if you remember, we got a matrix and we got these guys right here. We want to make those into ones, starting with the top left-hand guy. So I'm just going to work off this first row and I'm going to say, what can I do to this 4 to make it be a 1? Because that's my very first step. I need him as a 1 up there. So my answer for me is I can just multiply that top row by 1/4. Okay. I'm not adding it. I'm not swapping it. If this has been a 1 down here, maybe I would have switched them out, but it's not. So I'm just going to multiply that whole row by 1/4. And fortunately, they've got me some nice numbers here, so it's not going to be bad. 4 times 1/4 is a 1. This 4 times a 1/4 is a 1. And this -4 times a 1/4 is a -1. So that makes my top row there very nice. And I didn't do anything to the bottom row, so I'm just going to copy it. 5, 1, -17. I really recommend that you go back every time you copy a row and you make sure I copied it right, because that's where I said, like I said, I saw some issues, some people who made some mistakes there. Okay. Now I work off this first column first. This guy needs to be a 0. He's a 5. So I'm looking at that top column, top row, and I'm saying, what can I multiply 1 by and add it to a 5 to get a 0? Well, what can I add to 5 to get 0? -5, right? So I need this guy to be a -5. Now, I'm not changing that top row. Don't get confused by that. In fact, I highly recommend that you just go ahead and copy that top row. 1, 1, -1. Write him down. because we're not changing him. He's going to stay just like he is. But I'm going to multiply it by -5 and then add it to the bottom row. So the row I'm changing is row number 2. 5 times 1 is 5. I'm sorry, -5 times 1 is -5 plus 5 is 0. -5 times 1, still -5. -5 plus 1 is -4. And -5 times -1 is a +5. +5 plus -17 is -12. Okay. So again, keeping our end in mind, we want this diagonal to be all 1s. We want underneath to be 0s. This is only a 3x2, so it's not as bad as if I had a 3x3 matrix, the 2x2 equation. There were only 2 variables, right? So I only have the 2x2 matrix going on here with the augmented solutions out here. By the way, if you have to move a row, if you swap them, make sure you swap the entire row. That -12 better stay with this guy. Even if I move him to the top row, then the -12 goes with it. So take the solutions with it, is what I'm saying. Anyway, I want a 1 here. And again, I already have my 1 and my 0, so I'm just going to work off this second row. I'm not going to do anything to the top row, so I'm just going to copy him. 1, 1, -1. He is the way I want him, so I'm not going to change him again. But I'm thinking I need this to be a 1. So I need to multiply the -4 by something. Well, and it's going to be a negative, right? Because it's a -4. Negative times a negative is going to give me a +1, I hope. And to get this to be a 1, the 4 has to be multiplied by 1/4. So you can think, oh, I could divide by 4. Absolutely you can. And we do that by multiplying by a fraction. So 1/4. Negative times a negative is a positive. Oh, I'm sorry. We multiply it by 0, that stays the same, right? 0 times anything, 0. Negative times negative is a positive. 4 times 1/4 is 1. That's what I wanted. My diagonal is good now. And then a negative times a negative is going to be a positive. 1/4 times 12 is a 3. Okay. There we go. So now I have this diagonal the way I want it. Now I can read these equations. So make sure you can read a matrix straight off the thing. This is 1x plus 1y equals -1. And this guy is 0x plus 1y equals 3. So in my solution, I've got a 3 for the y right now. You cannot just say that the x value is a -1. You can't just pull this value. I saw a couple of you do that too, okay? I have to back substitute. You absolutely have to. We're going to use y equals 3 to do it, but I can't just say it's -1. So what I've got is 1x plus 1 times 3 is a 3 is equal to -1. So x plus 3 equals -1. And then solve for x, and that's stuff we've been doing all semester. So -3, -3, this guy goes away. X equals -1 minus 3 is -4. Okay, and that is why you can't just say it's a -1 because that was sitting there. It's not. It's actually a -4. So my x equals -4, my y equals 3. Okay. So that is one of those. You've got the 51 and 52 that have 3 variables, x, y, and z, but they end up working very similarly. I would use a matrix for that if I was doing it, just because that makes my life easier. And that's the biggest portion of this test 3 material. Notice that they've got some of those word problems on the very back. The exponential growth and exponential decay, where all you're doing is using the formula that they give you and figuring out what they want to know. So how much did you initially invest? I think that these problems don't go with that. Oh, it is, yeah. It's an investment problem. Okay, cool. For an exponential growth. How much money would you have initially invested? What percentage is the account increasing each year, and so on. So you have to use their equation and figure it out. I'm not too terribly worried about the word problems, but there you go. So that is it for our third day of review. I hope that gives you a good feeling for the test 3 material. That's the most recent material that we have. So hopefully that is the most fresh in your mind and not too terribly bad. And if you have questions or comments or need help, anything like that, sorry, there it is, it fell. Then just let me know, send me an email or something. All right, I will see you the week on the Wednesday, December 16th. No, not 16th. I'm so sorry. Finals week, what is it? I'm looking, I think it's December 14th. Yeah, December 14th, Wednesday, December 14th. I'll see you for a 2-hour final exam. All right, I'll talk to you later. Thanks. Bye.